Good morning. You're the first one.
No, we were actually waiting by the elevator.
Oh, sorry. I always come up the other stairwell so nobody ever sees me. It's always locked on. I feel like there's someone here who comes in on Wednesday evening and always ends up locking the doors. Just fine. I always kind of forget about that. So yeah. Cool. Good. People. Know how to take you. You turn on some lights. Really turn on some lights. So what should we talk about? I feel like we should finish up. There's a couple last things to talk about as far as I'm concerned with differentials and linearization stuff that we were talking about last time. And then I think we should probably start talking about graphing in general, finding extrema, whether absolute extrema or relative extrema. That seems to be where everyone is finally kind of getting to. So I think that'd be good. But let's talk a little bit about error propagation. So here's an example. Suppose the radius of a circle is measured with a possible error of plus or minus 3%. What is the resulting possible percentage error in the measurement of the area? So when we're thinking about percentage error, it's kind of the same as relative error. Oh, for those of you, sorry, Caleb, let me give you the attendance from here. So percentage error of something that's been measured is just essentially the change in the thing you're measuring, in this case, the radius divided by the total radius. And then sometimes we multiply it by 100 if you want it to be a percentage. You might think of this as delta R over R times 100, or you might think of it as dr over R times 100. Same kind of idea. So what we're saying here in this particular problem is we have that dr over R, over R is either plus or minus 0.03. Or you could multiply that by 100 and you'd be 3%. But we're not going to multiply by 100 until the very end. So we're just thinking of it as a relative change in, or relative, oh my gosh, words, the relative error. Now, yeah, another way to deal with this is to write it as an absolute value. We can say that the absolute value of dr over R is just 0.03. You might be saying, James said it was up to 3%. Yeah, I know I said it was up to 3%, but typically when we say that, we're just going to say that the error is the maximum possible error to make the calculations easier. I don't want to write that as a less than or equal to 0.03. I'm just going to write this equal to. Yeah, I just put them up here today. Sorry. So we're trying to find the percent change in area, meaning, or sorry, the percent error in area. So we're looking for this. We're looking for dA over A. That's what we're trying to find. So we're going to start with our differential. We're going to start with saying, well, we know the area of a circle is pi r squared. And we can find the derivative dA dr equal to 2 pi r. Okay. But what we really want is dA divided by A. So I'm going to say, well, dA is equal to 2 pi r times dr. This would be super easy, so I should point out, this would be a much easier problem to deal with if they told us what the radius was. And then you could say, like, the radius is 10 centimeters and the error is 3%. They didn't tell us that, which is okay, we can still deal with it. So we're going to now say that dA divided by area is equal to 2 pi r dr divided by area, pi r squared. And now look at what happens. This is kind of, I always thought this was super cool when I learned this the first time. I was like, oh, this is really neat how this always kind of works out nicely. If I start canceling stuff, the pi's cancel and one of the r's cancel. And I'm left with that dA over A is equal to 2 times dr over R. but we know that dr over r is the percentage error in the radius measurement. So we can say, oh, that's going to be equal to 2 times plus or minus 0.03, or if we still have some absolute values around things, the absolute value of this is equal to 2 times the absolute value of that, which is equal to 2 times 0.03. So 0.06. So what we're saying is, if the error in the radius measurement is up to 3% in either direction, the error in the area measurement is up to 6% in either direction. So our percentage error in measuring area is plus or minus 6%. It's kind of cool. The really cool thing is that this is kind of true. How do I say start? If you were measuring a length and calculating an area based on that length, the fact that you're kind of doubling the dimension means you're doubling the area. Let me say this another way. So for example, if we had done the same sort of thing, but said we had a square and we're measuring a side length, and the error in our side length measurement was 3%, the error in the square area measurement would be up to 6%. Basically, how much you're multiplying the power by is how much you're multiplying the error by. So let me ask you all, if instead, the same question, if instead we said measure the radius, but now we have a sphere, so then our radius error is still plus or minus 3%. And now what we're asking is, what is the percent error in measuring the volume of a sphere with that radius? So let me ask all of you, based on what I just said, what would you guess the error might be? No one's brave. It's okay. You don't have to guess. It's all right. You can think about your guess inside. Okay. So here's what I'm thinking. The volume of a sphere is 4/3 pi r cubed. So here's what I'm really actually going to say. If the here the radius is a dimension 1, here the volume has a triple that dimension, we're going to end up tripling the error, because this essentially you're multiplying that power by 3. It's kind of cool. So it's going to work out. Let's find. So we're going to find dv over v, which is just, well, dv is 4 pi r squared times dr, and the volume is 4/3 pi r cubed. So the dv part, right? That's just I could say, right, dv dr is 4 pi r squared. So dv is 4 pi r squared times dr. So then things cancel in a nice way. Pi's cancel, r squareds cancel, 4's cancel, and you're left with dr over 1/3 r, or if you prefer, 3 times dr over r. Oh, but dr over r is that 3%. So we've got that the absolute value of dv over v, that's the relative error in the volume, is equal to 3 times the absolute value of dr over r, which is the relative error in the radius. So that's going to end up equaling 3 times 0.03, which is 0.09. So the relative, or the percentage error in volume measurement, is exactly 9%. Which I think is super neat. So if you ever, like, if someone ever asked you, like, I measured this length and now I want to up to this amount of error, and what's the error in the volume, you just triple that error for any kind of thing. Yeah. So dv over dr is just, or as I would say, dv dr is just the derivative of volume with respect to r. So all I did is I just took the derivative of this and got 4/3 pi times 3r squared and canceled the 3's. Other questions about this? Okay, let's ask the question in the kind of opposite direction. Meaning, well, come on. Suppose the volume of a sphere needs to be measured to within plus or minus 8% accuracy. How accurate does our measurement of the radius need to be to ensure this? So really, we're just kind of going in the opposite direction, right? We need dV over V in absolute value to be, I'm going to say equal to 0.08, even though it's really less than or equal to 0.08, because we want it to be up to a maximum of 8%. And so then we're going to figure out what dr over r is going to be in absolute value. Same equations, right? I mean, really, we were just taking the same. V equals 4/3 pi r cubed. Our dV dr is 4 pi r squared. And then, what's going over here? Sorry. Terrible. And then we're going to say that dV divided by V, which is 4 pi r squared, dr divided by 4/3 pi r cubed, which simplifies to just 3 times dr over r. Some absolute values around just to make it nice. And then we know that we need this to be equal to 0.08. So we can solve for dr over r and say that dr over r in absolute value is going to equal 0.08 divided by 3, which is approximately 0.02777777. I think it's 77. Yeah, that's right. 6, sorry. 6 is apologies. Or if you prefer percentages, 2.66%. So our radius measurement needs to be accurate to within 2.66%, so that our volume measurement is accurate to within 8%. Again, seeing the same sort of relationship that the accuracy of volume is, or I should say the accuracy of the radius is 3 times as accurate as the accuracy of the volume. Kind of cool. I think I've always thought this was a neat fact about things. I'll say one last thing about this, just because sometimes it can be a little confusing. So let's say, yeah, sure. So one more example. We measure the surface area of a cube to be accurate, I can spell, to within 8%. How accurate is the measurement of volume? Good question. Okay, so I know how cubes work. The cubes look like this. I call my side length x. I know that the surface area of a cube is going to be 6 times x squared, and the volume of a cube is going to be x cubed. And here's what I know I have. I know I have that, I should just call this S instead of SA. I'm using too many things, or I could call it area. I guess I could just call it area. So I know that the area of my cube is 6x squared. So dA divided by A is going to be, well, dA is 12x times dx. So dA is going to be 12x dx over 6x squared, which simplifies down to just 2 times dx over x, which shouldn't be surprising because we know that the relative area and relative error in the measurement of the length, if you double that, it should be the relative error in the measurement of the area because the area dimension is twice the dimension of the length dimension. But we're trying to find a way of getting from this to that. So you could do the following. You say, well, I'm trying to find dV over V, right? Because that's what they're asked for. How accurate is the measurement of volume? So that's going to be dV, which is 3x squared dx, right? Right, yeah. dV dx is 3x squared. So dV over V is 3x squared dx over x cubed, which is 3 dx over x. So now what do I do? And I guess I could start throwing absolute values around things. I just put them everywhere.
If you don't put the absolute values, you get it wrong.
Depends on what you've said the problem is. Typically, it's more correct because usually we're talking about error being a plus or minus, so you can be above or below. So that's why we just write the absolute value to kind of not have to write that. So I would say you should write it, but if you didn't, it would probably not be the end of the world. Well, it's definitely not the end of the world. But. So we've written a bunch of things. We're trying to find this. We've got it equal to this. Do I know what dx over x is? Well, I can find it because dx over x is really just 1/2 of dA over a. So I could write this as 3 times 1/2 times dA over a. And actually, this is really what I wanted you to see. I don't actually care about the numbers, but I wanted you to see that this is equal to 3/2 times dA over a. And then, sure, dA over a is going to be, I didn't actually write it down, but it is 8% or 0.08. It's going to be 3/2 times 0.08, which is going to be 0.12 or 12%. Here's what I wanted you to see, though. From area to volume, so the area equation is essentially something squared. The volume equation is something cubed. And if you wanted to get from area to volume, you would need to raise this x squared to the 3/2 power to get to x cubed, which is exactly what you end up multiplying the error by. So the error amount you multiply by is always the power you need to raise to get from like the dimension you're in to the dimension you want to get to. It's kind of cool. I said like 3 times. It's kind of cool. I think it's neat. That's all I got for that. Questions about this?
Know that 3 ds over s is equal to 3 times dA over s.
So I'm taking what I did up here. So I know that dA over a is equal to 2 times dx over x. So then I replaced the dx over x with a 1/2 dA over a. Right. Well, because I'm replacing what dx over x is equal to. So I took this equation here and multiplied both sides by 1/2. So that 1/2 times the relative error in area is equal to the relative error in x.
Okay.
That's what I'm doing there. Other questions? Yeah. Sure. Right. So there's kind of 2 different things happening here. So typically, you're going to have either volume or area as some function of your length measurement, whether that's, for a cube, you're having, volume equals x cubed, area equals 6x squared, or for a sphere, you'd have, a radius, and your volume would be 4/3 pi r cubed, and your surface area would be 4 pi r squared. So there's kind of 2 aspects of this thing. The d whatever over the same whatever. So I should say, right, dv over v or dA over A, or dr over r slash dx over x. Those are all relative error or relative change in the thing you're measuring. So this just says, oh, that's the relative error in volume. And that's the same thing. That's the relative error in your measurement of the area. And that right there is the relative error or percentage error in the measurement of your radius or your x, whatever you want to call it. And so typically that's what we're given. So we are usually given one of these and asked to find another one. So in the previous problems, we were given that the error in measuring, say, the radius is some percentage, let's say 5% or 0.05. So right there, when I read that, I'm like, okay, I know that dr over r in absolute value, so we don't have to do plus or minus, is 0.05. And then we're typically asked to find what's the relative or percentage error in measuring some other aspect of the shape. So we want to find the relative or percentage error in measuring, let's do both, surface area and volume. So if I want to find the surface area one, which I should stop saying, right? I just write area because it's easier. So that means I want to find dA over A. So then I use the fact that, well, I know what the surface area of a circle is. Oh, sorry, of a sphere is. Surface area of a sphere is equal to 4 pi r squared. Which I'll just point out, because I've said before, it happens to be the derivative of volume. Only works for spheres, though, right? That's not true for a cube. The derivative of volume isn't equal to the surface area. Kind of neat, though, that works for cubes. Anyway, so then I want to find dA over A. So I'm going to take the derivative with respect to r. So I'm just going to find A prime, but I'm going to write it as dA dr, because that's what I'm finding. And that's going to be 8 pi r. And then I'm going to bring the dr over there to write the differential. So I'm going to say that dA equals 8 pi r times dr. And then I'm going to go back and rewrite this as dA, which I just found, 8 pi r dr, over A, which is 4 pi r squared. And what should almost always happen, because you're taking essentially the derivative of a thing with the power of r, and you're getting one less power of r when you take the derivative, is the thing on top should have one less power of r than the thing on the bottom. And so all the r's should cancel except for one of the r's on the bottom, meaning you'll be left with a dr over r, which we know what that's equal to. So that's the usual thing that will always kind of work out, is yeah. So this ends up equaling 2 times dr over r. And then we slap some absolute values over on everything, kosher. And then that's going to equal 2 times 0.05 or 0.10 or 10%. Which is what we expected because we knew we were doubling the dimension. And in the same sort of way, we should all expect that the error measurement in measuring the volume should be 15%, because we are tripling the dimension, so we are tripling the error. But we're tripling the dimension, so we're tripling the error. We're not cubing the error, right? It's not 0.05 times 0.05 times 0.05. It's 0.05 times 3, because we're just tripling it. Yeah, because that's how we usually get there. Is we start with the thing we know we have, and we try to work towards the thing that we start with. You're welcome. Yeah. All right. Other questions about this before we start talking about graphing in general, I guess, is really kind of where we're going next. Okay. Is it too dark in here? No? Okay. It's weird because you're all kind of like backlit with the sun, so it's like you're harder to see for me than you might imagine you are. It's fine. I don't really need to see you all. It's just I like to see you all. So lots of things about graphing, finding relative extrema, that kind of stuff. So let's start with Sure. Let's start with the extreme value theorem. Extreme value theorem. So the extreme value theorem says the following. If your function is continuous on some closed interval, say from A to B, then the function f attains both an absolute maximum and an absolute minimum. And they either occur at one, a critical point, that is a place where the derivative is equal to 0, or is undefined, or they occur at an endpoint. Graphically, here's a few examples of how this looks. You could have a function that look kind of like this. Where we're starting over here at a comma f of a, and we're ending over here at b comma f of b. This function looks like the way I've drawn it, but it has an absolute maximum right there at a critical point where the derivative is equal to 0, right? The slope of the tangent line there is definitely equal to 0. Or the other absolute extrema is right there. There's my absolute maximum. I'm sorry, minimum, apologies. There's my absolute minimum at the endpoint there. That is definitely the lowest point on the graph. You could also have, right? They could both end up being critical points. You get something that look more like this. I guess something that looks like that. They're going to be both, right there, right there. I'm gonna draw two more pictures really. You get something that looked like this, which I think is kind of cool. So your function looked like this, where you have a comma f of a, b comma f of b. Not that you really need to write these things in. I'll just point out again, right? Closed interval, the function's continuous. So we definitely have an absolute maximum at the right endpoint. And we definitely have an absolute minimum at this middle point where we have a critical point because the derivative there is undefined. So, right, you could have a point in the middle where the derivative is undefined. It's still, the function is still defined there. But I just want to point out that right there, f prime of whatever is undefined. You have a pointy point, as we like to call them, or as I like to call them. Really, what you call that is a cusp or a corner. It's a cusp specifically. So yeah. Another thing to observe is that if you don't have a closed interval or you don't have a continuous function, you're not guaranteed to get any of these things. Meaning, for example, just to kind of really be thorough, if the function is not continuous, nothing is guaranteed. You could have a function that looked like this. Be a little more specific with my function drawing here. Let's say it starts at the point 0, 1, maybe does something like this, and then does something like that. And ends at the point, I don't know. Let's say it's 5, 1. And this is the point 3, 2. And this would be the point 3, 4 if we had it. Sorry, you can't see that very well. Let me zoom in a little bit. This function certainly has an absolute minimum. It's got two of them actually. This function has an absolute minimum at x equals 0 and at x equals 5 with a value of 1. Oh, something to be careful about just in general. People ask for absolute minimum, maximum, or relative minimum, maximum in two different ways. They can either ask you where it is. So this function, the absolute minima are at x equals 0 and x equals 5. Or they can ask what it is. And this function has an absolute minimum of y equal to 1. So the points occur at the x value with a value of the y value. On the other hand, this function has no absolute maximum, which is kind of neat, I think. I've definitely had students before be like, well, James, isn't 4 the absolute maximum? Like, no, we never get to 4. You get really, really close to 4. No, so f prime wouldn't exist there. That's a really good question. Why wouldn't the derivative exist at this function at 3? Right, but there's a kind of precursor reason for that. And before we even talk about differentiability, we have to talk about continuity. And so what you should all remember or think about is that continuity is a requirement for differentiability. So if the function isn't even continuous there, there's no chance of even talking about differentiability. So yeah, it's not differential there because it's not continuous. On the other hand, continuity is not enough to say a function is differentiable, right? You could certainly have something like x to the 2/3 or the absolute value of x. Both those functions are continuous everywhere, right? These functions both are continuous everywhere, but are definitely not differentiable everywhere. Sorry, you can't see what I'm drawing probably. So both those are not differentiable at 0, even though they're continuous at 0.
And then also there's no absolute maximum because it's not continuous.
Well, yeah, right. So what I should really say is if this function were continuous, we would have had to have gotten an absolute maximum on this closed interval. But just to kind of go along with that theme, because there's something I want to make sure that's extra clear to everybody. Sorry, it's a weird way to block that off. It's also true if the function is on an open interval. So if we are not on a closed interval, again, nothing is guaranteed. You might not get an absolute maximum or an absolute minimum. Here's a really quick example of that. Let's say our function started, well, let's say it's on the open interval from 2 to 5. And it starts at the point 2, 1, except not really. It starts at the open point 2, 1, and it ends at the point, I don't know, 5, 4. Maybe it looks like this. So I'm going to ask you all a question that you might not like the answer to. Oh, that's 2, 4, not 2, 5, sorry. Does this function attain a minimum value? What's the lowest value this function has? Nope, definitely doesn't equal 1. It gets really, really close to 1, but not actually 1. At that point, it's not there because it's in an open interval. So I'm going to ask you again a question that doesn't have an answer. What's the lowest value this function gets? You might want to say 1.001. Like, well, what about 1.00001? Like, well, James, if I had more zeros, I'm like, well, where are you going to stop? The point is you can never get to a lowest value because no matter what value you pick, bigger than 1, I can always find a value that is smaller than that. It's still bigger than 1. So there is no smallest value. Likewise here, there is no biggest value. Be like, well, like 3.999, I can get bigger. 9, 9, 9, 9. Where are you going to stop?
If you have an interval with a function like x cubed,
Mm-hmm.
and you have a critical point, would that What would that,
So here's the thing. Here's what I'm trying to point out, and we'll get to this thing. You certainly could have an absolute maximum or minimum on an open interval. I'm just saying that the extreme value theorem only guarantees this thing if you both have a closed interval and a continuous function. So if we know that those two things are true, then we for sure get to have an absolute maximum and absolute minimum. If they're not true, you might still get those things, but you might not. Just to kind of point out another example. So here's another function on an open interval. Let's go from 2 to 5 again. And maybe it's starting, let's say it's starting at the point, sure, let's start at the point 2, 2. So not really, we're not gonna get that point. We're gonna go down to 3, 1. And then we'll go back up to like that. This is 4 again. So here's a function that's contiguous on an open interval, and it definitely has an absolute minimum, sorry. There's an absolute minimum at x equal to 3 with a value of y equal to 1. But there is no absolute maximum. Someone might say, James, what if you did 3.9999999 forever? And then I would say, well, sure. Not really, though. Because 3.999 forever is 4. Not like it's approximately 4, is actually 4. It's kind of weird, but it's true. So if someone ever writes this, like, or some teachers will prove to you in class, like 0.99999 forever is actually literally the same thing as 1. They are the same number. Two numbers are the same if there's nothing between them. There's nothing between the two numbers. But there's a very easy way to prove this, which people are like, I don't like this, but I'm going to show it to you anyway because it's fun. What's 1/9 equal to as a decimal? I'll give you a second. 9 goes into 10, 1 time, 1 times 9 is 9. Subtract, you get 1, bring down to 0. 9 goes into 10, 1 time, do the thing. It's a 1. It's 1 every time. It's 0.11111 forever. 9 is kind of great. 9 is a super cool number. 2 9ths, 0.22222222222 forever. 3 9ths, 0.3333. Oh, 1/3, right? 1/3, 3 9ths. So 0.1 something ninths is always just 0.222 forever. Now, here's where things are going to be kind of funny. Multiply both sides by 9. Well, 9 times 1/9 is for sure 1, but 9 times 0.11111 forever. There's never going to be a number that's bigger than 1 that we have to like carry something over to the next thing. So it's just going to be 0.9999999 forever. There's other ways of proving this too, but you should actually convince yourself that these are the same number. 0.9 forever and 1 are the same. It's kind of like, although not really, how 8 halves and 4 are the same number. It's just a different way of writing the same thing. Okay, enough about that. It's not that important, but it's always kind of interesting to talk about. You want to talk more about it sometime. We find that with our CP or our critical point. Yeah, so this, I'm assuming you're referring to this, Rhythm. You would find this point here because it's a critical point of that function, which we haven't actually defined this function, but we're about to get them. Yeah. So, oops, let me zoom back out a little bit. Oh, is it pronounced rhythm? Sorry about that. I saw an A, so yeah. Cool. Rhythm is one of my favorite hangman words because it's got like no vowels in it, except for the Y. Where it's like, what? No A-E-I-R-U? Okay. Anyway. Okay. What's that? No, what is it? Jazz. Interesting. I can see that. That's a good one. Yeah. Squishy is a good one too. No one ever gets squishy is hard in hangman because they're like a Q. And then no one's like an S, like it's, yeah, squishy is a good one. All right, anyway, back to math. So let's say we wanted to find the absolute extrema of f of x equal to x cubed minus 6x x squared on the interval from -1 to 7. So the idea here is we're going to find all the potential candidates for the extrema, meaning we're just looking for critical points and endpoints. So endpoints are obvious, they're -1 and 7. Critical points we find in the usual way, which I guess we haven't really talked about them in class yet, even though I've said it a few times. The way you find the critical point is take the derivative and find where it's either equal to 0 or undefined. There's a little bit of a caveat there, which we'll address shortly, but that's mostly it. So we're going to take our function's derivative, which is 3x squared minus 12x, and we're going to set that equal to 0. Or undefined, but we know it's never going to be undefined because there's none of the ways a function would be undefined in this particular expression. We're going to factor to make our lives easier, and we get 3x times x minus 4 equal to 0. So we end up getting critical points at x equals 0 and x equals 4. These are our critical points. So here's the deal. When you're finding absolute extrema, you take these critical points and endpoints and plug them back into the original function. Because we only care about which one has the biggest y value, which one has the smallest y value. That's it. So I'm going to find or evaluate f of -1, f of 7, f of 0, and f of 4. And I do strongly recommend that to make your life easier, you factor your original function as much as possible. Because I don't really know what 7 cubed is, but I definitely know how to calculate 7 squared times 7 minus 6. That's something I'm very capable of doing. So usually factoring is in your benefit here. So f of -1 is going to be -1 squared times -1 minus 6, which is 1 times -7, which is -7. F of 7 is going to be 7 squared times 7 minus 6, which is just 49 times 1. F of 0 is 0 squared times anything is going to be 0. And f of 4 is going to be 4 squared times 4 minus 6, which is 16 times -2, which is -32. So we would say that we have an absolute maximum at x equals 7 with a value of 49. Or to make your life easier, you could just say you have an absolute maximum at the point 7 comma 49. That kind of tells you all the information you want to know. Be careful if you're doing web work, right? Sometimes they'll ask for what the value is. Sometimes they'll ask where the absolute extrema occurs. And then our absolute minimum is going to be occurring at the point 4 comma -32. Or if you prefer, at x equals 4 with value y equal to -32. And we know we were allowed to do this because our function was a continuous function, it's a polynomial, on a closed interval. If it had been on an open interval, you couldn't just necessarily say, oh, well, these are going to be what we've got. That might not actually work out. Questions about this example before we do some more? I should say graphically, here's what this looks like. In fact, we can just kind of use our points. I've got the point -1, -7, which is something like this. And then I go up to the point 0, 0, down to the point 4, -32, and back up to the point 7, comma 49. It kind of looks like this. Which makes sense, right? It's a cubic function. It has kind of the usual cubic-ish shape. I just haven't drawn, right? I've stopped here. I didn't continue that way. I didn't continue that way because I only wanted the part that I was talking about. But that's what the whole thing looks like. All right, let's do some more examples. Yeah.
So whenever we want to find the critical points, we just equal But not only like the absolute.
No, yeah. So whenever you're finding critical points, you are always finding where the first derivative is either equal to 0 or where it's undefined. This one wasn't undefined anywhere, so we didn't worry about that, but we're looking for both of those things. And again, we'll be more explicit about that when we finally get to an example where we have to be a little bit more careful, which is coming up in a little bit here. So let's look at some more examples. Or unless there are other questions about this. Okay. Cool. All right. So let's look at, say, let's look at the following. Let's look at f of x equal to x over x squared plus 1 on the interval from 0 to 0 to 2 is so boring. Let's go 0 to fine. 2 is fine, I guess. I wrote 2. Not exciting, but whatever. Okay, so we want to find the absolute extrema. Actually, before we find them, let's make sure we can. Is this function continuous on the interval from 0 to 2? Well, it's a rational function. Rational functions are always continuous on their domains. So the real question is this function defined on the interval from 0 to 2? And it for sure is, it's actually defined everywhere because the denominator is never equal to 0 because it's x squared plus 1, which is always positive. So we're safe. Definitely we can use it because our function is continuous on everywhere, actually. So let's find the critical points. Oh, quotient rule. Quotient, yeah. Product, no, I was like, I'm saying the wrong thing. Product, wow. Which one are we using? Quotient rule. Bottom, derivative of the top, minus the top, derivative of the bottom, all over the bottom, squared. And this is why we actually want to spend some time simplifying things, right? Like a lot of the class we've been like, don't worry about simplifying, it's not a big deal. And that's usually true until you get to the place where you're trying to take this derivative and set it equal to 0. Because then you really want to be able to simplify your expressions to make it easier to solve. So specifically, I want to simplify the top. I've got x squared plus 1 minus 2x squared all over x squared plus 1 squared. Leaving things factored is to our benefit, so I don't want to multiply at the bottom, but I do want to simplify the top. Negative 2x squared plus x squared is a negative 1x squared. This is equal to 1 minus x squared over x squared plus 1 squared. You could write it as negative x squared plus 1. I don't prefer to do that. I would rather leave it like this and factor it like this. So I'm going to factor the top as a difference of squares, 1 minus x times 1 plus x over x squared plus 1 squared. And I want to find where that's equal to 0. I will say or where it's undefined, but just like the previous problem, this function is never undefined for any value of x, so I'm not going to worry about it. Okay, so my critical points are x equal to what two values? Somebody give me one of them. All right, yeah. What's the other one? Right. Okay, so now here's something to be aware of. When I'm trying to test all my points, I'm going to test f of 0, f of 2, f of 1, and not f of negative 1. Because negative 1 isn't in my interval. So you only want to test the ones that are actually in the interval that you're looking at. Negative 1 is not in the interval from 0 to 2. So we don't bother with it. I would say be aware of this. I've definitely seen questions on exams, asked questions on exams, where one of the critical points was outside of the interval, and I didn't want students to test that one. And if they did, they usually ended up getting the wrong answer because it ended up being the false extreme value. So be careful. All right, so plugging things in to my original function, right? Not to my derivative, but to my original function. F of 0 is 0 over 0 plus 1, which is 0. F of 2 is 2 over 4 plus 1, which is 2/5. And f of 1 is 1 over 1 plus 1, which is 1/2. Okay, I can definitely tell which one's the smallest. 0 is the smallest, so I have an absolute minimum at 0, 0. And I have, which one's bigger, 2/5 or 1/2? Right. And you can get a common denominator if you're not sure, or you can do the division, right? 2 divided by 5 is 0.4. 1 divided by 2 is 0.5. 0.5 is bigger. So there's my absolute maximum at the point 1, 1/2. Or again, you could say absolute maximum at x equals 1 with a value of y equals 1. Absolute minimum at x equals 0 with a y value of also 0. Okay, we'll do 1 or 2 more examples and then we'll move on to the next thing. Not that thing. Sure. 1 second, sorry. Think which way I want to go. All right. 2 more examples and I might take a bathroom break. Yeah. So let's look at this. Oh, I just turned the page. Sorry. Yeah, sure. So let's look at this example. F of x equal to x to the 2/5 on the interval from -1 to 32. Okay. So if I try and find the derivative here, find the critical points, I'm going to get 2/5 times x to the -3/5. And if I set that equal to 0, I actually don't get any solutions. There's no value of x that makes the thing equal to 0. So if I set this equal to 0, no solutions. If I instead say, well, where is this undefined? There is an answer. Because really I should be thinking of this as 2/5 times x to the +3/5. And then it's maybe slightly easier to see that x equal to 0 makes this thing undefined. So this is undefined at x equal to 0. That's where this function is undefined. So whenever you have x to a negative power, 0 to a negative power isn't 0. 0 to a negative power is what? Undefined. But it's still in the interval, and it's definitely a place where this function is defined, right? This function x to the 2/5 is a continuous function. It's defined everywhere. There's no weird breaks or anything. So definitely 0 is in the domain, so we're safe. So now we're going to test. So I'm going to look at f of 0, which is going to be 0 to the 2/5, which is 0. I'm going to look at f of -1, which is -1 to the 2/5, which is going to be positive or negative? Positive. +1. You can either do the squaring first and get 1, and then the 5th root of 1 is 1, or you do the 5th root first and get -1, and then -1 squared is +1. And then finally, f of 32 is 32 to the 2/5 power. You could go either way here too, but there's definitely a better way to go. If we do the 5th root first, the 5th root of 32 is 2, and then 2 squared is 4. The less good way is to square it first and get 1,024, and then to do the 5th root of 1,024 and get 4, because it has to be the same. I don't really know that the 5th root of 1,024 is 4. I just know that they have to be the same. So either way, we can see that great. There's your minimum. There's your maximum. So you have an absolute minimum at x equals 0 with a value of y equals 0. You have an absolute maximum at x equals 32 with a value of y equals 4.
Wait, for the -1 to the 2, how do we know if it's positive?
So here's the way it typically works. If you have a fractional power, if the numerator is an even number, you're always going to end up with a positive result. If the numerator is an odd number, you typically end up with the result that has the same sign as your input. 3/6 is a problem. So let's look. Give me 1 sec. Let's look at 3 different things. Let's say we could either have a power of like say 3/5, 3/4, 2/3, or I guess 2/4 is kind of funny though, because you could reduce it. So -1 to these powers is totally fine. -1 to the 3/5 power is, you can go either way. I like to do the root first. The 5th root of -1 is -1. Because -1 times -1 times -1 times -1 times -1 is -1. And -1 cubed is -1. On the other hand, -1 to the 2/3 power is -1 to the 1/3 squared. The cube root of -1 is still -1, because -1 times -1 times -1 is -1. And that's going to be 1. Okay, now here's where things get dicey. If I wanted to do, say, -1 to the 3/4 power, you're gonna have problems. What's the 4th root of -1? It's imaginary. Even roots of negative numbers are problems that we don't deal with. And even if you do the 3rd power first, still a problem. Because -1 cubed is -1, and the 4th root of -1 is still imaginary. So we can't deal with something like that. Can't have an even denominator when you have a negative base. So similarly, your question was -1 to the 3/6, same problem. We can't take the even root of a negative number. So it's not going to end up working out. It's kind of a bummer. If you had something like -1 to the 2/4, I don't know about that. That's extra dicey, because you could maybe pretend like -1 squared is 1 and the 4th root of 1 is 1. But I don't think you should, because really we can just reduce that power to 1/2 and then taking the square root of -1, which is imaginary. So again, you're not going to run into this, really, is what I should say, because no one's going to be like, here's this weird thing that doesn't work. But that's what we need to be aware of. So when if your denominator is an odd root, then the sign stays the same. And then if your numerator is an odd root, your sign still stays the same. If your numerator is an even power, sorry, I should say even power. If your numerator is an even power, your sign is going to become positive. If the thing that you're taking the square root of, or the whatever power of, is a negative number, it's totally fine if it's a positive number. For example, you can totally find 4 to the 3/2 power. That's going to be 4 to the 1/2 cubed, which is 2 cubed, which is 8. But it just does, yeah. So basically, the kind of real thing is you can only take odd roots of negative numbers. You can't take odd, sorry. Let me back that up. You can take odd roots of anything. You can only take even roots of positive numbers, is what I should say. You can't take even roots of negative numbers. Okay. Let's see. I thought I had another example, but let's look at one more. Let's say I want to look at f of x equal to, where'd you go? Sure. X over x minus 1 on the interval from 3, 5. Well, let's see what we get when we do this. The derivative is going to be bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. When we simplify this, we get x minus 1 minus x over x minus 1 squared. We can cancel an x, and we get -1 over x minus 1 squared. And this is never equal to 0. No. Where is it undefined? Right. And here's what I have to say. It's true. X equals 1 is not a critical point. The reason it's not a critical point is because it's not in the domain of the original function. So critical points are where the function is either equal to 0 or such as part of the rule. Critical points are where the derivative of the function is either equal to 0 or undefined at a point that is in the domain of the original function. This original function basically has a vertical asymptote at x equals 1. So you don't really have a possible max or a possible min or anything there. You have a vertical asymptote. What I'll say in addition to this is that even though x equals 1 is not a critical point, later on, when we start talking about the first derivative test and finding where a function is increasing or decreasing and stuff like that, it's still a point you want to include on your number line for the first derivative, even though it's not a real critical point. I often call it a pseudo critical point, even though it's not general. That's not like agreed upon terminology that other people use. It's just something I've come to call it, because it's still a point that's important to us that we want to put on our number line, but it's not a place where we can actually have a max or a min because it's the place where the function is undefined. Okay. Yeah, I should use the restroom. So let me give you all one to work on, just to have some one now. Just take a bathroom break. I'll be back in a minute. You all are welcome to use the restroom as well if you want. Asking what question you might have. Okay. Let's see. Is there a reason behind using the critical point in the first derivative test, despite it not being in our interval? Using the critical point. So we haven't really talked about the first derivative test yet. Typically, when we talk about the first derivative test, we include all the critical points because we're usually not limiting ourselves to an interval when we talk about the first derivative test. I know that's kind of a vague answer, but that's kind of the reasoning that I think that's kind of the question you're asking is there a specific example you're referring to with them or just general question? You're also welcome to say words if you prefer to. Okay, yeah. So typically, when we get there, when we use the first derivative test to kind of classify relative extrema, we usually use all the critical points, even if they're pretend ones like the ones I just talked about here. But yeah, and we usually are not limiting ourselves to a closed interval when we're talking about the first derivative test, because usually what we're going to be doing is, eventually the idea is to use all these things to help us graph a function more completely. That's kind of not the only thing we're going to do, but definitely one of the things we do is we want to be like graphing functions and finding their relative extremas to help us get a clearer picture of what their graph looks like. Yeah. Let's see here. Let me see if I want to say, yeah. We should talk about that. Before we talk about the first derivative test, though, we typically need to say some words about the mean value theorem. Have you all talked about the mean value theorem in class? Some of you yes, some of you no. Okay, so there's kind of two versions of it. One's just the kind of more specific version of this other general version. But here's what I would say is kind of the example we like to keep in mind when we talk about it. So here's kind of an interesting example. If you drive over a 1 mile long bridge or swath of road in 1 minute, and the speed limit on that bridge was 55 miles per hour, did you break the law? Did you speed? Good question. Did I speed? How fast was I going? Sure, on average at least, right? Maybe not the whole time, but definitely on average, my average speed was for sure 1 mile divided by 1 minute, which is really 1 mile divided by 1 minute times 60. Sorry, I'm doing my conversion wrong here. 1 hour divided by 60 minutes. And those cancel, and you get exactly 60 miles per hour. So yeah, I definitely sped. Maybe I wasn't going 60 the whole time. Maybe I was going like 40 part of the time and then sped up to like 80 at the end because I felt like passing someone who was going really slow. But the point is that if my average speed is 60 miles per hour, then my actual speed at some moment had to have been 60 miles per hour. Maybe I was going exactly 60 the whole time. Or maybe I increased my speed from 50 to 70 over the course of my 1 mile trip. Or maybe I started at 70 and decreased to 50. But somewhere along the way, I had to hit 60 miles per hour. Graphically, here's kind of what this looks like. So here I'm starting at the point 0, 0, where my time is 0 seconds or 0 minutes, and my distance is 0 miles. And then I'm going to end up at 1 minute later, having traversed a distance of 1 mile. So I'm going to end up over here. So there's my distance versus time graph. And maybe my distance looked like that. Like I was covering a lot of distance rapidly, and then I slowed down. Does this graph look like I'm slowing down or speeding up? I know I already said it, but it does look like I'm slowing down. The way we're thinking about this is I'm looking at distance versus time. So my rate of change or my derivative is my speed. And if we think about this over here, my speed is really kind of big, right? My distance versus time, I'm covering a lot of distance in a short amount of time. My slope of my tangent line is steep. Over here, my speed is slowing down quite a bit. My distance over time is not a lot of distance versus a fair amount of time. Now, here's what the mean value theorem says. The mean value theorem says that somewhere between here and here, somewhere between my endpoints, my average speed, I should say, not my average speed, my instantaneous speed is the same as my average speed. So my average speed is just my 1 mile per 1 minute, which is equal to 60 miles per hour. And somewhere along this line, the slope of the tangent line has to be the same. So there's a point right there where the derivative is equal to the average. And that's the gist of the mean value theorem in general. That if you have a function somewhere between your beginning endpoint and your last endpoint, the derivative of your function has to equal the average of the function. That's all the mean value theorem says. So let's actually codify that a little bit, but that's the idea you should think about. If you've got a function on some interval, all we're really saying is that if you know what the average rate of change is from the beginning to the end, somewhere in the middle, the function had to equal that average rate. The derivative had to equal that average rate of change. So here's the mean value theorem actually. The mean value theorem, often abbreviated as the MVT, just like the intermediate value theorem is often abbreviated as the IVT, says the following. If your function f of x is continuous on some closed interval and differentiable on the same interval except it's open, on the open interval from A to B. Basically, it doesn't have to be differentiable at the endpoints. It certainly could be, but it certainly has to be differentiable everywhere in between. Then there exists a number, usually we call it C, between A and B, such that, and actually let's draw a picture before we say what the such that is. So here's my picture, and maybe here's my A value, here's my B value, and here's my function. Maybe it's going to do something like this. If I went too far, that's all right. So what the mean value theorem says is there's some point between A and B where the slope of the tangent line is equal to the slope of the line connecting the endpoints. So here's my, I should use my ruler. I keep forgetting about my ruler. You can draw straight lines. So what we're saying is somewhere between A and B, there's at least one point, maybe more than one, where the slope of the tangent line is equal to the slope of that line. Or in other words, where the tangent line is parallel to that line. Maybe it's about right there. Or it looks like there's probably also one right there. So there's a C. There's a C. Mathematically, we say there is a C somewhere between A and B such that f prime of C, the slope of the tangent line at C, is equal to f of B minus f of A over B minus A. The slope of the line connecting the points, the endpoints. That is your mean value theorem. Or in other words, there's a place where the instantaneous rate of change is equal to the average rate of change. Which makes sense if you think about it, right? Because if you're, again, back to the driving example, you can't always go a speed that's below the average. Otherwise, your average wouldn't be the average that you said it was. Likewise, you can't always be above the average. You have to either always be the average, which is not very exciting, but then there's definitely lots of places where you equal the average, or you have to go from above to below or below to above. Here, I would say my speed, like if we're thinking speed, my speed's very, very fast. I'm going super fast, right? I'm going fast. And then I slow down, I hit my average, I slow down even further. I kind of maybe go backwards a little bit, I don't know. And then, right, I do it again. So there's not a lot of great questions typically that can be asked where you have to use the mean value theorem. There's a couple, which we'll talk about briefly here, but really the mean value theorem is a means to an end. We use the mean value theorem both in this class to talk about, and again, your mileage might vary. The professor might just be like, here's how the first derivative test works. Someone may be like, well, here's how it works. I'm going to prove it to you. I'm sure you all will have different experiences in your classes because some people really like to prove things, people don't. But we use the mean value theorem to help us prove that if a function is increasing, its derivative is positive, and if a function is decreasing, its derivative is negative, and vice versa. And then in Calc 2, 21B, we use the mean value theorem to help us prove how intervals work. So there's a whole lot of uses for it, but actual problems that make you use it are not very exciting. Here's an example of one of them. Find all values of C guaranteed by the mean value theorem for the function f of x equal to x cubed minus x squared on the interval from 0 to 4. So let me show you what we mean graphically again. X cubed minus x squared, let's see. So I could factor that. That's equal to, not that you need to graph it. I just want to graph it to show you. Oh, sorry. Did you miss something? Yeah. You're also welcome to grab these later if you want to. So this function looks like, let's see, I've got an intercept at 0, an intercept at 1, 2, 4. And it's going to do that kind of thing. We're bouncing there. Sure. So it looks maybe like this. And somewhere at 4 is probably equal to, let's see, it's going to be 64 minus 16, which is 48. You got the point 4 comma 48, and you've got the point 0 comma 0. And what the mean value theorem is telling us is that somewhere between 0 and 4, there's a point where the slope of the tangent line is equal to the slope of this line connecting these two endpoints. So somewhere, maybe right out there, I don't actually know where it is. I'm just graphically making it up. There's a point where the tangent line, well, I didn't really draw that very parallel, but where these two slopes are the same. The slope here is equal to the slope here. So our job is to find that point. Now, there could be more than one answer, because the mean value theorem says there's at least one such point, but there could be many. So while the theory here is moderately interesting, the calculation part is not that interesting. You're just going to find the derivative and set it equal to the slope of the line connecting those 2 points. So here are f of b minus f of a over b minus a is equal to, let's see, f of b is f of 4 minus f of 0 over 4 minus 0, which is just going to be, we already found it, it's 48 minus 0 over 4 minus 0, which is 12. So we're trying to find the place where the slope of the tangent line is equal to 12, aka we're trying to find a place where the derivative is equal to 12. So we're going to set f prime of x, which is 3x squared minus 2x equal to 12. And then we're going to solve. So solving that, we're going to have 3x squared minus 2x minus 12 equal to 0. And as much as you might wish it was true, it does not factor. You can spend some time trying to factor it. It doesn't factor. So if a quadratic doesn't factor, you get to use the quadratic formula. Like, yes. Like, fun times. So let's see, we get x equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a, which is going to be 2 plus or minus the square root of, let's see, 4. 4 times 3 is 12. 12 times 12 is 144. And it is a positive 144 because it's a negative times a negative. All over 6. So I've got something lovely. I've got 2 plus or minus the square root of 148 all over 6. Yeesh. So we know by the mean value theorem, there has to be at least one answer to this question. Actually, I should point out, we know because the function is certainly continuous and differentiable everywhere. So we certainly can use the mean value theorem, right? The function has to meet those 2 criteria. It certainly does. So there's at least one value, but there could be 2. So the question is, are both of these answers actually answers in our interval, or is one of them not? And I would argue one of them isn't. 2 minus the square root of 148. I don't know what that number is. I know it's negative. Square root of 148 is pretty close to 12. Right, it's close to the square root of 144. And 2 minus the square root of 144, or 2 minus 12 is for sure a negative number. So 2 minus the square root of 148 over 6 is definitely negative. And our interval is from 0 to 4, so that's not in the interval. So not in the interval. But the other one, 2 plus the square root of 148 over 6, must be. I'm not going to check, because I don't have to. Because the mean value theorem tells me I get at least one number. And since that one isn't it, this one has to be it. You could then make the internal mental argument that 148 is close to 144, and the square root of that is close to 12. And so you've got a number that's close to 2 plus 12 divided by 6, which is like 14 divided by 6, which is definitely less than 3. So we're for sure between 0 and 4, so we're safe. But you don't have to do any of that because the mean value theorem tells us that you get a number for sure. So those are the kind of questions that people typically ask with the mean value theorem. They're not very exciting. I'm going to show you one more though. Well, I'm going to show you the other type of question that you often get asked because your teacher might ask you this, or they might. I will say your teacher should not ask you this question on a test. I guess they could. Not this question. The next question. But a lot of them will ask you a question like this in your homework. So, two things we need. First, Rolle's theorem, which is just a special case of the mean value theorem. Rolle's theorem is a special case of the mean value theorem. It's the case where the endpoints happen to have the same value. So Rolle's theorem just says the same stuff as the mean value theorem. It says if your function is continuous on the closed interval and differentiable on the open interval, and the endpoints happen to have the same y value, then the rest is still the same. Then there is a number c. I should say that there is at least one number c. At least one number c between a and b. And I'm going to write this in an atypical way just to point out that it's really the same. Such that f prime of c is equal to f of b minus f of a over b minus a. It's just that in this case, what's f of b minus f of a equal to? Right. But it's still saying the same thing as the mean value theorem. We're saying that if you have a function that's continuous and differentiable on some interval, that there has to be a point in between the endpoints where the slope of the tangent line is equal to the slope of the line connecting the endpoints. It's just here, the slope of the line connecting the endpoints happens to be 0 because the endpoints are at the same height. So maybe your function looks like this. Or maybe it looks like this. But there has to be some place, maybe only one, maybe more than one, where the slope of the tangent line is equal to the slope of the line connecting the endpoints, which is 0. So that's what makes Rolle's theorem the special case, is that the endpoints happen to have the same value, so the derivative has to be 0. So, okay. All right, so now here's the question I want to ask you all. And I would maybe, I don't know, you're always welcome to write everything down. I would maybe not write this next one down just because it's kind of a giant pain. Let's take a look. So here's the question we were going to explore, and then we'll move on. Show that this equation, x cubed plus x plus 1 equal to 0, has exactly one solution. And we'll be a little bit helpful here. We will say that we're going to point out the solution lives between -1 and 0 to make life a little bit easier. Sometimes they won't give you that though. Sometimes they're like, so there's exactly one solution. So this is an important example in that well, it's kind of important. If you ever have to take like a math class where you have to prove some stuff, you might have to, like in 22A, you might have to prove some stuff. You'll probably have to prove some stuff in 22A. You might, depending on if you're like engineering, computer science, you might have to take an upper division like math 108 or something like that, where you probably have to prove some stuff. Or ECS 20, I think, you have to do some proofs too. This next example is an example of a very common type of proof, which is an existence and uniqueness proof. So to show that there's exactly one of something, you have to show that there at least is one. You have to show that one exists, and then you have to show that it's the only one. It's unique. So this is an existence and uniqueness proof. And we'll try and get through it quickly here. Again, I don't imagine anyone would ever ask this on the test because it's a giant pain. No one wants to grade this, but you certainly could ask you this on a homework question. So first, the existence part. How do we show an equation like this has a solution? We appeal to the intermediate value theorem. I don't know what the answer to this equation is, right? It's something between -1 and 0, but it's not like something nice. It's probably some terrible radical thing that we don't have a good idea of how to find. Totally solvable, by the way, just we don't typically deal with how to solve cubics in America. So if I want to show there is a solution, I'm going to use the intermediate value theorem. And the intermediate value theorem first relies on the function being continuous. So I would just say we're going to note that our function, which I'm calling x cubed plus x plus 1, is continuous everywhere, certainly on the interval of interest. Secondly, it goes from a negative to a positive value. If you plug in -1, f of -1 is -1 cubed plus -1 plus 1, which is just -1, which is negative. And f of 0 is 0 plus 0 plus 1, which is 1, which is positive. And if your function is continuous and it goes from a negative value to a positive value, it had to have gone through 0. So by the intermediate value theorem, since f of x is continuous and f of -1 is negative and f of 0 is positive, there must be some place between those two numbers. There must be a number c such that f of c is equal to 0. Oh, I forgot to say where c lived. There must be a number c between 0 and -1, or between -1 and 0, such that that function is equal to 0 then. We don't know what c is. We're never going to know what c is. Totally fine. No one asked us to find what c was. They just asked us to show that there was one and that it was the only one. Okay. That makes me think about the song about Tigers, right? Wonderful thing about Tigers is I'm the only one. Tigger, right? You know who Tigger is? Oh my gosh. Yeah, Winnie the Pooh. And the wonderful thing about Tigers is I'm the only one. I'm the only one. I'm the only one. Anyway, it's a fun song. It's a good song. It gets stuck in your head sometimes. So we've shown that there is at least one solution to this equation, but we haven't shown that it's the only one. So typically the way you show that there's only one of a thing is you say, well, pretend there's two. And then if you pretend there's two, you're going to get to some place where you have some logical fallacy. Typically called a proof by contradiction. Assume the thing that you want to show is true is actually not true, and then get to some place where you say, well, the thing I assume being not true means something bizarre that can't happen is happening. So my assumption must have been false. So for the uniqueness part, we're going to assume there are two such solutions. Call them A and B. Even though we call this other one C, I know. Call them A and B. Okay, so if there's two solutions to the equation, we're calling them A and B. That means that f of A must equal 0 because it's a solution to the equation, and f of B is equal to 0 because it's a solution to the equation. Okay, seems fine so far. So now we're going to appeal to Rolle's theorem. So I've got two functions. I've got two places on this function. They're equal to each other. They have the same height. Specifically, they're on the line, right? So graphically, I'm saying I've got A and B here. Maybe my function does something like this. I don't actually know, but it might do something like that. And by Rolle's theorem, there's got to be a place between A and B where the derivative is equal to 0. So let's check that out. So by Rolle's theorem, there is a number between A and B. Let's call it X, such that f prime of X is equal to 0. Like that. Okay, but now here's where we're going to run into a problem. My derivative is 3x squared plus 1. And if I set that equal to 0, there is no solution. No real solution anyway. Right, because you're going to get 3x squared equal to -1. That's not going to work out. This has no solution. But Rolle's theorem says there has to be a solution. So it must be that our assumption of two answers to this original equation is false. Right? That's the thing that was leading us to be able to use Rolle's theorem, which was leading us to this conclusion that the derivative had to equal 0, even though it can't.
What if we're given like a function that crosses A, for example, but then it like has a derivative of 0, and then it goes back down, and as x approaches infinity, it just approaches 0. You know, it never crosses 0.
I guess then, well, prove what?
That it only crosses, that it only has one solution.
Let me think about that for a second. So just before I think about that, to sum up here, we would say, so our assumption of two solutions to f of x equal to 0 must be false. And that shows that we have one solution, and exactly one solution. We do not have more than one solution. So let's see. I'm trying to think about your question there. So your question is like, how would we show, for example, so how to show, I'm just thinking of that. Let's see, let me think for a second here. That should work out just fine. That f of x equal to, sure, let's say x minus 1 over x plus 1 squared equal to 0 has exactly one solution. Something, is that kind of what you're thinking of?
I don't know, I'm thinking about it graphically.
Sure. So am I. So here's what this looks like graphically. We've got a vertical asymptote at -1, and it looks like this. If x is 0, -1 over 1 is -1. What's this?
Yeah.
And we definitely got that intercept right there. So how would you show that this equation has exactly one solution? It's a good question. I don't know if I have an answer off, like a thought process off the top of my head of like what you would do. Yeah, like how do we know that x equals 1 is the, I mean, graphically, it's very obvious, I think, right? Graphically, sure, it doesn't equal 0 anywhere else. Plus it. I suppose, yeah. I mean, I suppose you could look at this and say, well, if this, I suppose it's easier if your thing's not polynomial. If this equals 0, then we have to have the x minus 1 equals 0. And the only solution is just x equal to 1. So I think the context that we were working in before was we've got some cubic polynomial, and it might not be super clear to us if that crosses the x-axis once, twice, or 3 times. But yeah, I don't have I don't know if this is problematic or not. Like, I don't know if we could really need to use Rolle's theorem to try and do this thing. We probably could. It just feels to me like we probably wouldn't need to. Let me think for a second here. I don't know. Something like that. I don't like this example particularly that I just made up because it's not continuous everywhere. But yeah, I'm not sure. I don't know if that question, I don't imagine that question would really come up, but that doesn't mean it's not worth exploring. So yeah, I don't know. I would maybe, if I was trying to phrase this question in the kind of way that you are, I think, thinking of it, I might, because the problem is you don't have a closed interval. So you don't know if you can really use Rolle's theorem or the mean value theorem, because the mean value theorem, you have to be limiting yourself to a closed interval so that you can find the slope between the two endpoints. And here, if we're trying to go out to infinity, that's not really a thing that we have. So I like the way you're thinking. I just don't think it's really something we can address with the theorem we just talked about. Yeah. So I don't know. I don't have a good answer to the question I just made up. Other than just setting equals 0 and solving it and finding the only solution.
So in like a problem like this that you're talking about, you need a closed interval then?
If you're talking about using the mean value theorem or Rolle's theorem, yes, we have to be using a closed interval, because the mean value theorem depends on saying that there is a place where the derivative is equal to the slope of the line connecting the endpoints. So we have to have endpoints to be able to connect them, to be able to use the mean value theorem, which means we have to have a closed interval to have those endpoints. Yeah. Excuse me. So let's see. We only got a few minutes left here. So here's what I'll say is what's coming up. Talk about next week. A reminder: no class tomorrow. Not that we have class in general Friday, but you don't have class tomorrow. It's not a school day. Don't come to class. Enjoy a 3-day weekend. So here's what's coming. Is the first derivative test. The first derivative test for relative, also known as local, extrema. So the difference between a local and an absolute extrema is that an absolute extrema is either bigger than everything else on the graph or smaller than everything else on the graph or on the function. Whereas a relative or local extrema is just bigger than or smaller than all the stuff immediately next to it. That's the difference. So, for example, if I want to find the relative extrema, meaning maxes or mins. So we usually use the word extrema to say maxes or mins because we don't want to find the relative maxes and the relative mins. Find the relative extrema for f of x equal to x to the 4th minus 4x cubed. Just like with the extreme value theorem, the idea is that local extrema will occur where we have critical points. So either where your derivative is 0 or where your derivative is undefined. I would encourage you to keep, like, these are the examples I kind of keep in my head. Like, for example, y equals x squared, right? We have a relative minimum at the origin. It's also an absolute minimum, but it's a relative minimum because it's less than all the stuff around it. And also another good example is y equal to the absolute value of x. Both of these functions have relative and absolute, but I only care about the one part here. Both of these have relative minima at the origin. And I would point out for y equals x squared, what's the derivative of y equals x squared at the origin? Yeah, right? Y prime is 2x. And if we plug in the origin, y prime evaluated at 0 is 0. Here, what's the derivative at the origin? Does not exist. So here, y prime of 0 definitely does not exist. still totally possible to have a relative extrema there. Because it's definitely smaller, right? That y value is definitely smaller than all the y values immediately adjacent to it. So to do this, we find the critical points. And so f prime of x is 4x cubed minus 12x squared. We set that equal to 0. And we factor because we can. Factor out a 4x squared times an x minus 3. And we're going to get x equal to 0 and x equal to 3. So both of those are critical points. And maybe we have a maximum at one of them, a relative maximum. Maybe we have a relative minimum at one of them. Maybe we don't have either. So that we check to see if it's a relative maximum or a relative minimum or neither, is we use the number line for the first derivative. So I'm going to draw my number line. And on my number line, I'm going to put my critical points. So 0 and 3 and nothing else. And then I'm going to ask myself, okay, in each of these 3 intervals, is my derivative positive or negative? This is why we also like to factor, because it makes it easier to determine if the derivative is positive or negative. So if I pick a number like larger than 3, like 4, and plug it in, 4 squared is positive, 4 minus 3 is positive, the whole thing is positive. And then you can either just keep plugging in points, or you can say if I look at 3 came from this factor has an odd power, so the sign is going to change. If I look at 0 came from this factor has an even power, so the sign is going to stay the same. It's always true, by the way. If you come from a factor that has an even power, your sign stays the same. If you come from a factor that has an odd power, your sign changes.
I have another theoretical
Sure.
question. If we have a function like the cube root of x, and you have an undefined
Derivative.
derivative at like where
At
it's
0.
up, yeah, vertical. How would that be any kind of extrema at all?
It would not in that case. Let me show you. Let me answer that question very soon with 2 quick examples. But yeah, so this one here, the reason we make this sign chart is because then we know, and we'll talk more about why we know this next class, that if your function's derivative is negative, the function was decreasing, increasing. So at 0, we don't have a relative extrema because the function was getting smaller and then kept getting smaller. But at 3, we have a relative minimum. So f of x has a relative or local minimum at x equal to 3. Because it was getting smaller before 3 and then getting bigger after 3. So at 3, it bottoms out. And the general idea is that if you go from decreasing to increasing, you have a relative minimum. Whereas if you go from increasing to decreasing, you have a relative maximum. And we'll definitely specify that more next time. We'll actually write a formal definition, but that's the whole idea. So, and you can even kind of draw your function. Like what's happening here is you're getting smaller. Maybe you level out for a second, you keep getting smaller, and then you start getting bigger. Oh, look, there's a minimum there at 3. There isn't a minimum here at 0. It's kind of like on the graph x cubed when you flatten out for just a second at the origin before continuing upward. It's actually an inflection point, but we'll talk about that another day. To answer your question, so here's 2 examples. F of x equal to x to the 1/3 and f of x equal to x to the 2/3. Both of these have derivatives that are undefined at 0. F prime of x equals 1/3 x to the negative 2/3, which is 1/3 x to the positive 2/3. And definitely x equal to 0 is a critical point. Here, same deal or similar deal. The derivative is 2/3 x to the negative 1/3 or 2/3 x to the 1/3. And likewise, x equals 0 is a critical point. The difference is one of these is going to have a relative minimum, one of them is not. So this one, if I look at the sign chart for my first derivative, Well, if I plug in a number bigger than 0, like 1, 1 to the 2/3 is positive, and the whole thing's positive. If I plug in a number like -1, actually, this is where your question from before is actually really pertinent. If I plug in a number like -1, -1 to the 2/3 power is positive or negative? Positive, because we're squaring it. So we're increasing. This function doesn't have a relative extrema. It looks like this. f of x to the 1/3 is your usual cube root. It looks like that. Oops, come on, James. It looks like that. As a vertical tangent, because the function has a derivative that's undefined, but it doesn't have a relative extrema there because it keeps increasing before and after. On the other hand, x to the 2/3, if we look at the sign chart for the first derivative, well, now if I plug in something bigger than 0, like 1, 2/3 times 1 to the 1/3 is positive. But if I plug in something like -1, -1 to the 1/3 power, or the cube root of -1 is just -1. So when I plug in a negative number, we actually get a negative result. And so that means my function is decreasing and then increasing. So I do have a relative minimum at x equal to 0. Graphically, this function looks like this. I call it the bird function. It kind of looks like a bird that you might draw as a young person, like that. But we definitely have a relative minimum at the origin here, where the function is, where the derivative is undefined. So hopefully that answers your question. It was a good question, and I think this kind of answers it.
Yeah.
Cool. So last thing I'll say here is that typically figuring out if you have a relative max or a relative minimum comes down to the first derivative test. Just making the sign chart for the first derivative and then seeing if your function is decreasing, increasing, or increasing, decreasing. That'll tell you if you have one. There is something else called the second derivative test for relative extrema, which we'll talk about another time. But even if you learn that one, this is still the better way to do it. So I would say if you ever have to find a relative max or relative minimum, this should be your default go-to of how you do it. Yeah, stop talking now, for real. You're welcome, brother.